The 2017 solar eclipse is nearly upon us. The path of totality will travel across 14 states, starting in Oregon and ending in South Carolina, and may trigger what some have called a zombie apocalypse across the contiguous U.S. as people flood the roads, skies and rails to travel to their viewing locations. While the celestial event will be spectacular, and, for many, a once-in-a-lifetime opportunity to see the disk of the sun completely blocked by the moon, most eclipses don't involve the sun and the moon at all. Astronomers use chance alignments of celestial bodies to study objects in our interplanetary backyard and those orbiting distant stars. Total solar eclipse 2017. When, where and how to see it safely. When an object passes in front of a star, it's called a stellar occultation. Astronomers can predict when these occultations will happen and then observe these fleeting eclipses of distant stars. Stellar occultations occur when a celestial body completely hides another as seen by the observer. Kimberly Smith, project scientist at the Stratospheric Observatory for Infrared Astronomy SOFIA, told Space.com. Occult, from the Greek, means to block out. SOFIA, a modified Boeing 747 SP aircraft that carries a 2.5-meter (8.2 feet) reflecting telescope to observe the universe in visible and infrared wavelengths, is very adept at tracking down occultations, which may be visible only from certain locations depending on the object's position. The Airborne Observatory is a partnership between NASA and the German Aerospace Center and is based at NASA's Armstrong Flight Research Center in Palmdale, California. It flies at high altitude, above most of Earth's atmosphere, that can have a blurring effect on ground-based astronomical observations, and can be used to fly in the path of an occulting shadow wherever it may happen around the world. SOFIA is a unique tool to observe these events because we can bring SOFIA to intercept the shadow of an occultation event, especially if it is over water, where we cannot have an equivalent ground-based telescope, Smith said. A recent example: the next target for NASA's New Horizons spacecraft, which famously flew past Pluto in July 2015, is 2014 MU-69, an object in the ring of icy bodies beyond Neptune known as the Kuiper Belt. The object was set to drift in front of a star on July 10, completely blocking the pinpoint of starlight. SOFIA collaborated with dozens of ground-based telescopes to observe the event, and it was able to fly into the tiny and fast-moving shadow of 2014 MU-69. By studying the brief disappearance of starlight, SOFIA astronomers can compare their observations with others and measure the size and characteristics of the otherwise invisible object, Smith said. Occultations of stars can be caused by many celestial objects, Smith added. These objects include asteroids, moons including Earth's moon, and even dwarf planets and trans-Neptunian objects beyond Neptune's orbit in the outer solar system. Also, Trojans, asteroids that follow along a planet's orbit, and Centaurs, objects with characteristics of both asteroids and comets, can be studied as they pass in front of stars. These are excellent opportunities to measure the size shape of the body blocking out the background star, search for or confirm the presence of rings or other satellites about the object, confirm its location in the sky, and confirm or provide limits to an atmosphere about that object, Smith said. NASA's Airborne Observatory SOFIA measured the Kuiper Belt object 2014 MU-69 as it traveled in front of a distant star. The object is the next target for the New Horizons spacecraft, which flew by Pluto in 2015. Credit NASA. Whereas occultation studies use distant stars to help scientists learn about mysterious objects in Earth's solar system, astronomers can also look for eclipses occurring in distant star systems to reveal information about alien worlds many light-years away. NASA's Kepler Space Telescope is one such mission that looks for the eclipses caused by extrasolar planets, or exoplanets, that dim the light from their stars. If these exoplanets' orbits are aligned just right, Kepler detects a very slight dip in star brightness as the exoplanet drifts in front of the star from our perspective. This is known as a transit. And although the dip in brightness is nowhere near as dramatic as that from a solar eclipse as seen from Earth, or as sudden as an asteroid occulting the pinpoint of starlight, these distant eclipses reveal fascinating insights about exoplanets of all sizes. NASA's Kepler Space Telescope finds hundreds of new exoplanets, boosts total to 4,034. You can learn two main things during an exoplanet transit. The amount of light being blocked will tell us the size of the planet, and the frequency by which the light is blocked will tell us the orbital period of the planet, or how long it takes to orbit its star, said astrophysicist Geert Berenson, guest observer office director of NASA's Kepler and K2 missions at NASA's Ames Research Center in Mountain View, California. Launched in 2009, Kepler's prime mission was to stare unblinkingly at one region of the sky, toward the constellation Cygnus, continually monitoring the brightness of over 150,000 stars. It was an incredible success and found over 2,000 confirmed exoplanets and more than 4,000 candidate exoplanets, Berenson told Space.com. When the second of 4 gyroscope reaction wheels inside Kepler malfunctioned in 2013, however, the Space Telescope lost its ability to point at the single region of the sky. But by using the slight pressure of sunlight exerted on the spacecraft's body, NASA scientists came up with an ingenious plan to stabilize the spacecraft enough to begin a new mission, called K2. Since 2013, Kepler has been used to survey different parts of the galaxy, Berenson said. So not only did K2 give us more exoplanets, we are now at about 160 confirmed exoplanets from that mission, but we are also able to survey different parts of our galaxy. Eclipses aren't caused only by planets, exoplanets, asteroids and moons, Berenson noted. During Kepler's mission, the spacecraft has been able to observe eclipses not only between planets and stars, but also between stars and other stars. Because many of the stars in our galaxy are known to orbit together in binary pairs, a situation may arise where one of the stars in the orbiting pair may drift in front of its partner from our perspective, just as an exoplanet transits its host star. And though Kepler may be better known for its exoplanet hunting prowess, it's also a prolific eclipsing binary hunter. Kepler has discovered thousands of eclipsing binaries so far, Berenson said. Studying eclipsing binaries is very important for models of stellar evolution. Star clusters, for example, are known to contain stars of various masses and luminosities, Berenson said, and if scientists can calibrate our view by measuring eclipsing binaries, they can precisely measure the star's physical sizes and further develop these stellar evolution models. Total solar eclipses have been useful to scientists for centuries. When the moon blocks the glare of the sun, fainter objects surrounding the sun become visible. One stunning example is the revelation of faint scattered light emanating from the sun's magnetized corona, the sun's hot, yet very tenuous atmosphere. As the moon blocks the sun from view, solar astronomers will take the opportunity to observe the delicate detail in the sun's extended magnetic field. In addition, planets in our solar system will be visible during the daytime as the sky goes dark during totality, a natural occurrence that astronomers try to replicate when seeking out distant exoplanets. When people are going to look at the total solar eclipse, during totality, they will in fact see Jupiter, Mercury, Venus and Mars, because the light of the sun will be blocked, Berenson said. And this is the exact same method that NASA is going to be using in the future to study exoplanets. You can see these stars and planets during the 2017 total solar eclipse. This method is known as direct imaging, and it differs from the transit method of exoplanet detection in several key ways. Direct imaging works the same way as eclipses are used to observe the sun, Frank Marchus, senior researcher and chair of the Exoplanet Group at the SETI Institute in Mountain View, California, told Space.com. We simply block, or occult, the bright light coming from the star, so we can see the faint features surrounding the star. With transits, on the other hand, changes in the star tell researchers about the planet. Marchus works on several exoplanetary projects, including the development of the Gemini Planet Imager (GPI) instrument that is located at the Gemini South Telescope in Chile. The imager can precisely position a device called a coronagraph to block a star's glare, revealing the faint light coming directly from exoplanet atmospheres. The GPI and tools like it create fake eclipses to better see the faint objects orbiting distant stars. Direct imaging means that you get photons coming directly from the object, Marchus said. When you get photons from an object, you don't see the shadow like you do in a transit, you see the object itself. You can derive the temperature of the object, the composition of the upper atmosphere. In some cases, researchers can also use the data to learn about clouds and haze at the top of the atmosphere, he added. And because GPI observes stars specifically with infrared light, it could potentially detect the infrared signals of methane and water in the planet's atmospheres. As the technology and observational techniques become more sophisticated, Marchus said, scientists are on the verge of directly imaging a bona fide Earth-like planet. The aim isn't to survey for exoplanets, it's to detect just one exoplanet like Earth, to get the pale blue dot of our generation, Marchus said. He suggested that Alpha Centauri, the nearest neighboring star system to our own including red dwarf star Proxima Centauri, which is less than 4.4 light-years away, could be a target to search for such a world. Moreover, the image of its discovery would be as significant, if not more so, than the famous pale blue dot photograph of Earth taken by the faraway Voyager 1 spacecraft. If there is a small planet orbiting Alpha Centauri, and astronomers can photograph it, that photo will motivate the next generation of astronomers, he said. that will motivate them to build better instruments, to be more imaginative, to design new technologies, to be able to detect and characterize Earth-like exoplanets. Marchus is currently working on the next generation of direct imaging instruments, called TIKI, that could be attached to existing ground-based observatories such as the 8-meter aperture 26 feet telescope at Gemini. But things will get interesting over the next few years, when planned large mirror observatories such as the 30-meter telescope and the extremely large telescope go online, he said. High-contrast coronagraphs and large aperture telescopes will be capable of spotting planetary systems containing small exoplanets around nearby stars. There are also some very big exoplanetary missions that will launch to space soon. In the near term, we have the TESS Transiting Exoplanet Survey satellite mission launching next year, which is going to do a much wider survey of the sky than Kepler, so we're going to find lots more planets around bright nearby stars, Berenson said. And also, next year, the James Webb Space Telescope is going to launch, and it will hopefully be able to look at the atmospheres of exoplanet targets discovered by both Kepler and TESS. Further in the future, there's going to be the space telescopes WFIRST, LUVOIR and HABEX, which are very much in the study phase. Those telescopes will be able to use a coronagraph to block the light of the host stars so they can see the photons directly from the exoplanets, he added. So, on August 21st, if you have the opportunity to see the moon totally eclipse our sun, remember that there's more to eclipses than what happens to our nearest star. Eclipses of celestial objects happen all the time, giving us invaluable new insight into objects that we'd otherwise never see. Follow us at space.com, Facebook or Google. Originally published on space.com.